Okay, we're back, folks. So this is the third lesson for the first week, and the quiz on Friday at 9 o'clock on D2L will have basically some stuff from all of this. Okay, so the stuff that's on the board you probably don't want to write down just yet because I was looking at some of the problems we were working on in class, and maybe we didn't do enough of those. So ignore all of this for now. I'm going to leave it up there and I'll erase it. There's some additional problems in the last section that I can just help set up for you. We did 4 of them, so we did number 5. So there's one there with density. Okay, and that'll actually be helpful. So density is mass over volume. Okay, that's fine, you've probably seen that before. So we would take 1.49 grams. And actually, I'm just gonna kind of set this up. So if we take sort of density, in this case, it's gonna be mass over volume. It's 1.49 grams over 2.8 cubic centimeters, which is the same thing as 2.8 milliliters, but it's a solid object. Now, you can calculate that, grams per cubic centimeter, and get an answer. That's fine. And so that you combine that into one thing. And then this asks you to convert it into pounds per cubic feet. Okay, I'm just going to set this one up. So we have to convert the units in the numerator and the units in the denominator. So just pick one. Grams into pounds should be pretty straightforward because we know 453.6 grams is 1 pound. I'm going to double check that this is recording. I think it is, but it's going to look awful silly if I forgot to do that. Yep, it's recording. Again, you don't have to do it with the numbers separated like this. You can just have one number and then do math. It's actually probably easier. So grams per cubic centimeter, do the math and put an answer here. Okay, I'm not going to actually calculate this. Now if you go from cubic centimeters to cubic feet, well, I know that 2.54 centimeters is equal to an inch. And I'm going to cube that. So that'll be centimeters cubed. We'll cancel that, so then we have inches cubed. And we also know that 12 inches equals 1 foot cubed. I sometimes find people they'll forget to cube the 12, they might square it to 144, but it's cubed. This is the one I screwed up before. This is like 16 point something or other. And I think that's right. So you'll have grams going to pounds. You'll have, let's see, inches going to cubic centimeters, and then inches going to, so the answer here will have something or other pounds per cubic feet. I don't know what the answer is, but that's how you would set it. Just make sure you don't cube this, obviously. Well, I don't know if that's obvious or not. You cube this one and this one, but not this one. So you get that answer. From the periodic table, a mole of gold has 196.97 grams. I think you can do that one, but that's something we're going to talk about later. So if you have 5.6 grams of gold, you would divide that by 196.97, and that'll give you how many moles of gold there are. And remember how to go from a mole to an atom? You would multiply by 6.022 times 10 to the 23rd, because that's how many atoms are in a mole. So you'll divide the mass by what's called the atomic mass, 196.9, and then multiply by what's called Avogadro's number. So you can set that one up. Number 7, the volume of a certain bacterial cell, this is actually something similar to the quiz, is 2.56 cubic micrometers. I think you can do that one. I'll just do the 2.56 cubic micrometers. So 2.56 cubic micrometers, so it's pretty small, it's a bacteria. And you want to go to cubic millimeters. Okay, this is a good one, because I don't think you want to do this in one step. This is one where you want to go to the unit without the prefix and then go to the next one. So we know that a micrometer is 1 times 10 to the minus 6 meters. cubed. Wow. -6 raised, this is going to be to the -18th power. So you multiply those two, so that'll be a cube, so I guess I can write that down. So a cubic micrometer is 1 times 10 to the -18th cubic meters. I think that's right. You don't have to do this step, just put that on your calculator properly. So a micrometer is 10 to the -6 meters. And then you go to millimeters, we know that 1 millimeter is 10 to the -3rd, or 1 times 10 to the -3rd meters cubed. I think that's right. So micro is 10 to the -6, milli is 10 to the -3rd. So those units will cancel. And we'll be left with cubic millimeters. Now let me just show you a little bit of this math here. So this is 10 to the -18th. This is going to be 1 cubic millimeter is 10 to the -9th. Let me get rid of the 1 here. It's a little confusing. All the extra writing. I think that's right. Yeah, 10 to the -9th. Now, -18 in the exponent here at -9, this is going to be -18 minus a -9. All this is going to end up being 10 to the -9 as a conversion factor. So it's going to be, if you get the answer, I think you should get this on your calculator. Just double check it to make sure I did it right. The answer should be 2.56 times 10 to the -9th cubic millimeters. I think that's right. Okay, so you can check that one. And the last one, converting meters per second into miles per hour. I think if we need to do that one, we may save that one for class. Okay, so the video is already getting a little too long, too much of a long start. So let's switch over. The last topic I think is pretty quick. I'll say that a lot, I might not always be right. So on the PowerPoint slides, I think the next heading is called Uncertainty in Measurement. And I've been teaching chemistry now for a long time, and sometimes this particular topic is one of the least popular, is how do you report answers? You do a bunch of calculations, and how do you report them? I think this is a hugely important topic. And we call it significant figures, but it's bigger than that. The reason we talk about this is because when you report an answer based on laboratory measurements, your answer can only be as good as your least precise or your least good quality instrument. And in some cases, if you don't follow these rules, you're misrepresenting your data. You're either selling yourself short or you're saying you have a degree of precision that you don't have. Think about that in a laboratory setting, like for medicine or for environmental analysis. If you're not paying attention to proper reporting of answers, that can have some pretty severe consequences. So I know these rules are pretty dry, but they're pretty important. So you're not just randomly writing down answers. Okay, so here are the rules for significant figures. The rules we follow for reporting answers. Really, there's two things we need to know. And you don't have to write down all this, you can write it. I think I might even have it on the slides here. Let me just scroll down. I'm looking at the PowerPoints, by the way. Yeah, and the example I used here is a density object. That's fine. I'm going to come back to that case study that I have. I'm going to cut to the chase. Significant figures, we mentioned them. How do you know if a measurement, what digits are significant? The only real question is when are zeros significant and when are they not? These are rules you need to know. So I've broken them down into these rules. You can look at the book, look at this a million times, but let's wait for examples. So if you have zeros at the front of a measurement, those are not significant. That doesn't mean they weren't measured. That means they don't tell you anything about the sample. So for instance, that zero before the decimal place, that zero, those are not significant. Non-zero digits are always significant. So what we do is we take away the ambiguity, we put it in scientific notation. We call this 5.3 times 10 to the minus 4 grams. I guess that would be 530 micrograms? No. Yeah, okay. So that's fine. So you put it in scientific notation, only showing the digits that are significant. So this measurement has 2 significant figures. Contrast that with what are called trailing zeros, zeros at the end of a measurement. We have 2 cases, if you have a decimal point or you don't. Mathematically, those 2 measurements are exactly the same, 5,300 pounds and 5,300.00 pounds. Scientifically, they are universes apart. If a digit is recorded in this manner, a value is recorded in this manner, you have no idea, is that measured, or is it a placeholder? If you put a decimal place and 2 more zeros, you're indicating that you measured that very, very precisely. So this has 2 sig figs. We don't know if those zeros are significant, and we would write this 5.3 times 10 to the 3rd pounds. I'm going to save some time. Always write the units. We don't write those zeros as significant. These, however, are significant. 1, 2, 3, 4, 5. This has 6 significant figures. Those zeros matter scientifically. And we would actually write this, even though it looks like it's not saving any time. 5.3, 0, 0, 0, 0 times 10 to the 3rd pounds. Again, mathematically the same, scientifically vastly different. So leading zeros, pretty straightforward. Trailing zeros, whether or not there's a decimal place, I don't know. I think I called this when I was a high school teacher. Most high school science teachers I know do this. Zeros in between other non-zero, they are significant. That's okay. So, yeah, all right. So we would write this one as 6.30031 times 10 to the 2nd millimeters. You don't have to put that one in scientific notation. I'm just doing this to illustrate a point. Also, I occasionally see this. Some students come into a college class. Every time they write something in scientific notation, it's always digit point something, and they only write 2 sig figs every single time they do that. I'm not sure why that happens. I'm going to blame physics teachers. Just a joke. So make sure that when you put something in scientific notation, you write all of the digits which are significant. And those are the rules for zeros. Calculations, I'm just going to illustrate this. Most of what we do in chemistry, with a couple of exceptions, is multiplication and division. All those unit conversion problems that we already did, those are all multiplication and division. Those are easy. Take the sig figs with the number you're given, write the answer with the same number of sig figs. Easy. 5 to start, 5 to finish. 2 to start, 2 to finish. 1 to start, 1 to finish. If you take 2 things that are not just a conversion factor, you do the math and report your answer to the least number of sig figs from whatever you're multiplying and dividing. So if you've got 2 sig figs, 8 sig figs, 25 sig figs, your answer has 2. For multiplication division, you go by decimal places. This number has 10 decimal places, this answer has no decimal places, you subtract the 2, no decimal places. Okay. So that's what you do. And then the last thing is pay attention to order of operations. You do plus and you do typically do addition subtraction first before you do this, and take care of your sig figs along the way. All right. I don't think I have a ton here. If you're writing notes, this is letter B, and we don't call it this in Gen Chem, but when you take measurements and you do calculations, every time you do a calculation, the error propagates. It gets bigger and bigger every time you do the calculation. And for really small measurements, the error gets huge. So sig figs are an example of that. Yeah, okay, so I have this case study of density here. All right, you can read that. You've got an analytical balance and a 25 milliliter grad. Well, the analytical balance is better. So the grad cylinder is going to limit our answer here. That kind of makes sense. I'm just going to jump to the last one. So we're doing water display. This is like middle school physical science. Take an object, measure its mass, put some water in a cylinder, drop it in there, measure the difference. Okay. I'm just going to quickly do this one. So density is mass over volume. In this case, the math is mass. Excuse me, math. We don't calculate mass typically, we just write it down. And to get the volume of the object, we subtract the volume. So 14.5 mils minus 12.0 mils. Well, let's apply the rules. So that has 4 sig figs. The 0 is not significant, so that's 4 sig figs. This has 3 sig figs. Since the decimal place is there, that also has 3 sig figs. You want to be able to do that. Identify the sig figs in a measurement. I'm not going to do a bunch of those. There's a ton of them in the book. So we follow order of operations. We have to subtract first before we do the division. So we subtract those two, and the rule is decimal places. So 1 decimal place, 1 decimal place. Sweet. You write your answer with 1 decimal place. Well, that's kind of weird. So actually, it's not. Why am I even thinking about it? That's 2.5 mils. Notice what happened here. We went from 3 sig figs down to 2 sig figs. We lost 1. That happens all the time in lab when you do 2 things that are different. You subtract 2 things, you now lost some precision in your calculation. Propagation of error. Not all the time. In this case, yes, we lost a sig fig. So, you jam that on your calculator, and you're only going to write, see, it's a division. So we've got 4 sig figs and 2 sig figs. Our answer only can have 2 sig figs, that's it. So I would write this as 0.18 grams. I'm just going to do this to make a point. Since it's a solid object, we typically don't use milliliters for a solid object. I'm just going to switch over and use the equivalent unit of cubic centimeters. We already know that milliliters. Now, some students don't like this because they say, but my calculator gave me more digits than this. My calculator actually gave me 0.18252, depending on what calculator you're using. Well, yeah, but that would be a lie. If you wrote 0.18252, that number is a lie. You did not get that precision from these instruments. You got that precision from these instruments. So this is not correct. Sometimes what's done, it's kind of old school, is you write the significant digits like this and put the ones that are not significant. But most books don't do that anymore. So we don't have to really worry about that. So this has 2 sig figs. All right. I'm not sure how much more I want to do with this, because you just have to do it on your own. You have to use the book. The book does a good job. Yeah, okay, we did all the rules. Okay, we've got those. Yeah, okay. You know what? I'm gonna skip ahead. I'm gonna skip ahead. So these you just want to work with. I'm going to see if I can finish off this chapter with this lesson, okay? So on the slides, we can work on those problems in class, or you can come to my office hours and we'll do those problems. What I want to do is skip ahead on the slides. Excuse me. To the table of data. I think if I figure all this out on your own. Sorry, this is a real mess. This is going to look a little messy here to wrap things up in this first chapter. So take a look at those 2 sets of densities there. So 2 students go in, or 2 technicians go in and do a density experiment. Again, not a very exciting experiment. And they generate 2 sets of data. And we know that the density is supposed to be the true value. You don't usually know what the true value is. is 0.53 grams per milliliter. I'm just going to kind of talk you through accuracy and precision. This is more of a lab thing. We may do some of it. So there's the data there. So if you're looking at two sets of data, which one's better? Well, better means two things. Did you get the same answer over and over again, like you should? If it's a good scientific method, it should give you the same answer every time. Within reason, of course. That's called precision or reproducibility, okay? If you know what the answer is supposed to be, like you have some kind of a standard, which we'll talk about in the lab, how well does it match the standard? Well, that's accuracy. Okay, well, which ones? Now, how do you know? Well, take a look at it. Data set number 1 looks pretty reproducible to me. 0.62, 0.59, 0.60, that's very reproducible. But it doesn't look very accurate. In fact, if you take the average, which is what you would do, of course, if you take the average of data set 1, you're not going to get 0.53. If you take the average of data set 2, you'll get much closer to 0.53. So do that if you want to. So data set number 1 is definitely more reproducible. Data set number 2 is definitely more accurate. So no one data set's better there. That's really hard to say. You want both. You want accuracy and precision, not going back. In lab, you're going to learn a couple things. I'm giving you a little bonus here. Precision, we have a way of measuring this, a way of calculating this called standard deviation. And accuracy is measured by something which you probably know. It's called percent error. I'm not going to put the formulas up here. That's a lab thing. And we're almost done. I think I already mentioned, I'm on the last slide. Yeah. Conversion factors don't affect the sig figs. That's fine. You report the answer with the same sig figs. And the last thing I want to show you here are the temperature scales. So, how do you do this? The formula for degrees Fahrenheit and degrees Celsius. Typically what you do is you put Fahrenheit on the y-axis, Celsius on the x-axis, and we know 2 points make a line, and we know we can actually put 2 points on here. The freezing point of water and the boiling point of water, 0 and 100. I don't know how often you know this. So the freezing point of water in Fahrenheit is 32, so we put this point here. And the boiling point of water in Fahrenheit is 212. I don't know if you know that. So we can put, oops, that was dumb. So we can put another point out here. So 100, 212, 032, and whoa, wow, that was terrible. And you make a line out of that. And then if you remember your algebra, I need to take some cobwebs here. Let's see, y equals mx plus b, point slope formula. So y here is degrees Fahrenheit, x is degrees Celsius, b is the y-intercept, which is 32, and m is the change in y, so y2 minus y1 over x2 minus x1. So it's what y2 minus y1. So 212 minus 32 over 100 minus 0. And I think we can leave it like that, can't we? I think that works. So degrees Fahrenheit, you can derive it, is 1.8 degrees Celsius plus 32. I think you can put that into a fraction. Is that 9.5? Divide each by That works. The other one, the Kelvin one, this is kind of cool. I just think this is neat. This is not really a derivation, this comes from an experiment. So I'm just talking you through this. So you take a sample of gas, then you measure its pressure. This is just a thought experiment. There's actually some high school labs that I've seen where you can do this. We used to do it. And you measure the pressure of a sample of gas, which is just a measure of how fast the molecules are moving and how fast they're banging into each other, they're colliding with one another. And you raise the temperature. So think about a rigid container of gas and you're going to crank up the temperature. What's going to happen to the pressure? It's going to go up a lot. It's kind of dangerous. So pressure and temperature are directly proportional. It'll go up like this. Jack up the temperature, the pressure goes up. Well, we measure that in Celsius. Pressure is a measure of molecular motion. If we extrapolate this down here, that in principle would be the temperature where no molecular motion takes place. It goes down to zero, zero pressure. That is called absolute zero. No molecular motion, and that happens to occur at negative 273.15 degrees Celsius. So we define a new temperature scale. The Kelvin temperature scale is your degrees Celsius plus 273.15. Good to know that. And folks, that is the end of the first week. If we're doing a flipped classroom, I think that's it. Let me just check my notes. Okay, that's it. So the quiz is not going to have temperature conversion. The quiz will have significant figures, and the quiz will have unit conversions with Greek prefixes and conversion factors, which I will give you. So that should round it out. Nice work.